Hey there class, in this crucial video today we are talking about something called calorimetry. We have been talking briefly about heat, right? The transfer of energy that takes place between different substances because of a difference in temperature. Well, how can we actually measure it? We can measure it with something called calorimetry, okay? And what calorimetry is it's that measurement of the heat that is involved in a physical change or a chemical change based on a change in temperature. And there is, of course, an equation that goes with calorimetry. It's right here. Q equals M times C sub S delta T. Now, what this is it means that the heat involved, which is often in joules, you can convert it to kilojoules, but it's often in joules, is equal to the mass of the substance that we're heating up in grams. Its specific heat, which we will talk about what that is in just a moment, but it has units of joule per gram times degrees Celsius, multiplied by the change in temperature, where the change in temperature is the final value minus the initial value. Now, just to make a note, heat we've been saying is measured in joules, and that's true, it is measured in joules, but it also could be measured in calories, and there is a relationship for us to take this little calorie here and relate it to food calories, and we can look at that at another time. But in 1 calorie, there are 4.184 joules, so there is a conversion factor there. And then this specific heat thing, whatever it is, and we'll get to it in just a moment, is an intensive property. It can be used to identify something because it does not change based on amount. Now, as a quick note, it should go without saying that if we heat up a substance, we make its temperature go up, so it has a delta T greater than 0. And if a substance cools down, its delta T is less than 0. Well, just to show you briefly what this equation would look like in action, suppose you heated 50 grams of water, which has this as its specific heat, 4.18 joules per gram times degrees Celsius. And it heats from 25.4 degrees Celsius to 71.3 degrees Celsius. How much heat was absorbed by the water? So you can see I've run out of room a little bit, but I've made my no-want table based on the values that have been given to me here, and then I've set it up and I've plugged it into my equation. So when we're doing math, we should really do 3 things. We should write the equation once, we should write what we're plugging into it, and then we can write the answer down below. And you see here that when I do this, everything is going to cancel out except for joules, which is what I want. And when I type it into my calculator, I get 9,593.1 joules, or based on the 3 significant figures, that it should be 9,590 joules as my final answer. So we can use this equation to calculate simply the amount of heat involved in heating up a substance or cooling down a substance. But what on earth is this CS thing, this specific heat? Well, specific heat, as a definition, is the amount of energy that is required to raise 1 gram of a substance by 1 degree Celsius. And when you think about its unit, it should make some sense. Joules per gram degree Celsius. It is the amount of energy to raise 1 gram by 1 degree Celsius. So that's why those are paired together on the bottom. This helps to explain for us why different substances heat up at different speeds. Why is it that a copper pot is going to heat up a lot faster than the water inside it? Well, it's because water as a liquid has a pretty high specific heat. That's actually a pretty high value for this concept, whereas copper has a much lower specific heat. Okay, so that means if we take a sample of copper and a sample of water, and we have the same mass amount of them, and we give them the same amount of heat, we allow them to absorb the same amount of heat, that the water is going to have a smaller change in temperature because it has a higher specific heat. Okay, this also assumes that they start at the same initial temperature as well. But we can use this concept to help us figure out when we might have a larger delta T depending on a substance given in a heat change, okay, in a heat transfer that takes place. So specific heat is an important concept, and I really need us to conceptually hopefully understand that if we have a very small specific heat, such as copper, that means it only takes this many joules to raise 1 gram of copper by 1 degree Celsius, whereas it takes 4.184 joules to raise 1 gram of water by 1 degree Celsius. You'll also notice here something a little bit bizarre that might strike you, which is that water has 3 different specific heats, and that's because it does matter, it does depend upon the state of matter, and we will look at that a little bit more in depth when we do phase changes and the heat involved in phase changes. So then how on earth can I measure heat, or can I do calculations with respect to heat when I have two different objects at different temperature. Now, we know that heat flows from hot to cold. And so if I have an object at a very high temperature and an object at a lower temperature, and I put them into contact with each other, that heat will transfer from hot to cold until they reach thermal equilibrium, which is the same temperature, right? So how can I use my knowledge now that Q equals mc delta T to help us out with this? Well, what we want to think about is the fact that whenever a heat transfer happens, one thing is going to absorb heat and one thing is going to release heat, okay? Especially when those objects have different temperatures, right? But they always reach the same final temperature because that's what thermal equilibrium is. So even though this is going to observe the law of conservation of energy, the amount of heat absorbed will equal the amount of heat that is released, the objects themselves can have different delta T's. They can have different temperature changes because the heat is also dependent upon the mass and the specific heat involved. So let's look at a sample calculation here, where a 10-gram sample of copper metal is heated to 75 degrees Celsius, and it is placed into a 100-gram sample of water at 25 degrees Celsius in an insulated container, meaning that no heat is lost from the container. What is the final temperature of the metal? It's also going to be the final temperature of the water. It's just not saying that. Assume no heat was lost when the metal was transferred. Well, we can set up this equation and plug in the mass-specific heats and initial temperatures for the metal and for the water into this equation. But let's first set up our no-want table. Okay, so when I make my no-want table, and apologize, it's a little hard to read over here, I am pulling out my mass, my specific heat, and temperature values from this. Now, I just grabbed the specific heats from the previous page instead of giving them to you directly in the question. But hopefully we can agree that if we're putting a hot piece of metal into water, the temperature of the water is going to go up, and the temperature of the metal is going to go down. Hopefully we can also agree that this final temperature, whatever it is, should probably be in between these two values, right? So let's find out what that final temperature is. Now, as a quick note, I changed Q1 equals negative Q2 here to indicate the heat transfer to QH2O equals negative QCU. It does not matter whether you'd put QCU over here and negative QH2O over here. But to emphasize that it's the water that's going to go up in temperature because it has the smaller value initially, and the copper is going to go down because it has the higher initial, I wrote it this way. But in reality, it really doesn't matter because you can always divide or multiply by -1 to just move the sign over. But I take QH2O and then I just treat it like Q equals mc delta T. I plug in everything that I know. I know the initial mass of, or the mass of water, the specific heat of water, and I know the initial temperature. Over on the other side, you have to be so careful about this negative sign. So it's the mass of, that's why I have brackets here. It's the mass of copper times the specific heat of copper, and then multiplied by the delta T. Please be so careful. Don't worry about this negative sign maybe until you've solved this entire side and then can distribute it through. But the rest of your question should then look something like this. So then what we do is just algebra. So multiplying similar terms, then distributing through, doing that on both sides, distributing the negative side gives us eventually this line here. And then we combine like terms. I'll combine the things with the variables on one side of the equation and the integers on the other side of the equation. And then I solve. I'll divide both sides here by 421.85, and I get that my final temperature is 25.5 degrees Celsius. And that might seem surprisingly small, but again, water has a really high specific heat. Its temperature is not going to change very much, especially compared to something like copper that has a much smaller specific heat value. And this value is in between the two initial values, so that fits with what we should expect. This is our final temperature when we've reached thermal equilibrium. So there are two more types of calculations that we should be expected to be able to do with respect to calorimetry. One is called enthalpy of solution, which is also occasionally called enthalpy of dissolution because it's about the process of dissolving. So when a solid dissolves in water, right, even though it can technically be classified as either a physical or a chemical change, I like to think about it as a physical change. What is happening is that sometimes heat is transferred between the solid and the water. It is either the solid, when breaking apart and forming new interactions, is going to release heat to the water and the temperature of the water goes up. Or it's that the solid requires heat in order to dissolve, and so the temperature of the water will decrease, okay? Because the heat of the water will go to the solid to help it dissolve. Now, here is the issue with this. It often takes place in what's called a coffee cup calorimeter, which is exactly what it sounds like. It's using, unfortunately, styrofoam cups, and we have this double styrofoam cup, so there's one cup within another cup here, and then a lid that's on it. There's a space for a thermometer, a stir stick that moves up and down in order to stir the solution. But what happens is you add the solid and you stir, and you have already recorded the initial temperature and you record the final temperature to figure out what it is. Now, when we are measuring the temperature, we are not measuring the temperature of the solid. We're measuring the temperature of the water, and that's the solution, and that's part of the surroundings here. So with this sort of process that is taking place, this is an interesting one because there is no barrier between systems and surroundings. There's no barrier between, like there is between two objects being in contact with each other, right? We could define one of the objects as the system and the other one as part of the surroundings. We can't do that here, okay? There is no barrier that is present. And so since we're not directly measuring the heat absorbed or released by the solid, we need to use the value of the solution of the water data in order to calculate what the change is. And we'll look at that in just a moment. As a quick note, oftentimes on the AP test, you're given a calorimetry question and you're asked to do two things. You're asked to first calculate Q, and you're asked to secondly calculate delta H. Oftentimes, not every time, oftentimes, when you're asked to calculate the value of Q, it specifically says magnitude. That means don't worry about sign. Just calculate Q equals mc delta T. But if you are asked to calculate the delta H of solution, the enthalpy of dissolution, or for that process, then you must include the sign. But let's look at an example with this question, and I will keep this picture here as well. So you're a student. Let's say that you investigate the enthalpy of dissolution, or the delta H solution, for the solid KOH, and it collect the data below. So you have this data in this table right here. What I want you to do is I want you to calculate the delta H solution in kilojoules, and then I want you to calculate it in kilojoule per mole of KOH. Well, the same thing is true here. It is still going to be a heat transfer that takes place in which one thing is going to absorb heat and one thing is going to release heat. When we have enthalpy of solution that is being asked for, here's how I want us to think about it. I want us to think about it as the delta H of solution that we're calculating is equal to negative Q. And that Q is of the solution that is in here. So we are measuring the temperature of the solution in this coffee cup calorimeter. Okay, we're solving for this, but we're measuring this. So we can use the information in this table to then help us out. So the delta H solution is going to equal negative mass of solution, the specific heat of the solution, and the delta T of this solution. As a quick note, oftentimes, if water is the solvent, which it almost always is, then we just use the specific heat of water, okay? Yes, the solid that dissolves in here does have a little bit of an influence on this, but we always ignore it, okay? So instead, we're just going to use this. So when we go to type this in to our calculator and write this out, I want you to see something here that might look a little bit strange, okay? The mass of the solution that we use is the mass of the solid and the water combined, because what we want is the mass of the solution of the whole thing. And once the solid is added to the water, we've created this solution. Remember, there's no barrier between the solid and the water itself. It starts to spread out throughout the whole thing. So we must use the mass of both of these things added together in this case when a solid is dissolving in water. And so that's grams, and then multiply this by 4.18 joules per gram degree Celsius. And this is multiplied by the delta T, the final minus initial, which should be 13.5 degrees Celsius. And when I do this, I get for my delta H solution, I'm going to get negative 5,988.92 joules. Now, I wanted it in kilojoules, so we would need to divide this by 1,000, which is going to be negative 5.99 kilojoules for delta H of solution. Now, the second thing that it asks is it wants it per mole of KOH. As a quick note here, we used 6.13 grams of KOH. Hopefully we agree we can use the molar mass of KOH to find how many moles of KOH we had. We did not use 1 mole of KOH. So what we're going to do is we're going to find the mole amount using the gram amount here and the molar mass, and then we're simply going to divide. We're going to do this kilojoule amount divided by the moles of KOH to get what it would be for kilojoule per 1 mole of KOH. So we have briefly talked about reactions that happen in aqueous solution. Now, with acid-base reactions especially, oftentimes they involve a heat transfer. In fact, oftentimes they release heat. So let's look at this example here. A student mixes a 10 milliliter sample of 1 molar NaOH aqueous with a 10 milliliter sample of 1 molar HCl aqueous in an insulated container. The temperature of the solution before mixing was 20 degrees Celsius. That is including both of those together. They were both at the same initial temperature. If the final temperature of the mixture is 27 degrees Celsius, what is the experimental value of delta H of reaction? And then it says to assume the solution mixture has a specific heat of 4.2 joule per gram times Kelvin, which is just like 4.18, okay, except for, so we're pretending that this is just the same value as for water. And then the only difference here is Kelvin. Now, don't freak out because Kelvin's here and degrees Celsius is here. You're not going to make any changes, and I'll show you why. But it also tells you this. The solution mixture has a density of 1 gram per milliliter. Now, why is that important? Okay, so very similarly to what we did on the other page, we have a Q1 equals a negative Q2, okay? Or in other words, in this case, delta H of reaction is equal to negative Q, okay? We're measuring the enthalpy change of this reaction that happens, okay? With this, it should make some sense then that what I'm going to do here is I'm going to plug in a mass amount for the solution that is based on the density value there. And the reason why I can do that is because I have 10 milliliters and 10 milliliters, which means 20 milliliters. If the density is 1 gram per milliliter, then that's going to be 20 grams that I'm using in my solution, okay? Specific heat is 4.2 joules per gram, and I'm going to write Kelvin here. And then in terms of temperature, actually, I'm going to change that to degrees Celsius. But in terms of temperature, hopefully you agree, we're measuring delta T, which is change in temperature, and a change in temperature of 5 degrees Celsius is the same as a change in temperature of 5 degrees Kelvin, as an example, okay? So the change is the same, regardless of if the numbers that are initial and final would be different. That's why we can kind of substitute Kelvin in here into this question, or use degrees Celsius as well. And so with this, then that's delta T is going to be 7 degrees Celsius. I'm going to plug this in, and then I'm going to solve. And so when I do, I get negative 588 joules as my enthalpy of reaction, my delta H reaction. Now, if you're a little bit hung up on this setup that takes place on this question and the previous question, I just want to stress that, do we agree that the temperature of the water, of the solution, increased, the delta T increased? Which means this value of Q, ignore that negative sign for a second, but this value of Q here is a positive value, okay? It's 588 joules. Well, that had to come from somewhere. Where did it come from? The water absorbed the heat from the NaOH and the HCl reacting with each other, okay? So that's why we are always going to have, for when a reaction happens or when a solid dissolves in water, a delta H sub something equals negative Q, okay, in order for us to do this, because we're measuring the temperature of the surroundings, and the reaction is the system, or the dissolving is the system in the case of a solid dissolving. Okay, that is everything I have for you in this screencast, okay? Please don't hesitate to let me know if you have any questions, but we're going to do some good practice with this. Thanks very much.